All right. Okay, everybody, settle down. So, welcome. So today we're going to pick up where we left off on Thursday. So if you remember, we were talking about scheduling, and okay, keep the murmuring down. And if you remember, the discussion of scheduling was really around this loop that we just keep constantly selecting a new thread, running it for a period of time, going back, selecting a new thread, and that's scheduling. And the question is sort of, how do you do that? And we were starting to talk about goals for scheduling. So among other things, the goals for scheduling aren't always compatible with each other. Okay? So for instance, we might want to minimize response time if we have a highly interactive system. And the response time is literally what the user sees, right? So that's like keystrokes, the time you press a key to when it shows up on the screen, etc. Or in the case of real-time tasks, which we're going to talk about separately a little later today, responsiveness could be important because it could impact physical things, okay? So like your brakes. The other thing that's not necessarily compatible with minimizing response time is maximizing throughput. So here, maybe in the cloud, you're trying to maximize the number of operations or jobs per second. It's related to response time. So if you make your CPU faster, your response time will be faster. But, that just goes without saying. But if you're really keeping the CPU the same and you want to maximize throughput versus minimizing response time, those are different scheduling policies, okay? And maximizing throughput, by the way, is obviously minimizing overheads. You don't want to waste anything. And it's also about efficient use of resources. So for instance, the longer you run, the more likely you are to get good cache state, etc., good CPU resources, okay? So which of the schedulers we've talked about so far is likely to really do a good job on throughput? FIFO, right? Because you're just running that sucker straight through. All right. And then fairness is this other weird thing, which who knows really what fair is, because there's a lot of different versions of fair. Fair with respect to a user, fair with respect to threads, etc. Some way of sharing CPU among users in an equitable way ultimately gets into this notion of fair queuing, which we're going to kind of bring up a little bit later. But fairness is not minimizing average response time, because better average response time makes the system less fair. And I'm going to tell you about a funny example of that a little bit later. But think of this. If I'm trying to make sure that whenever I type, I get CPU, if you sit there and you type really, 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 really fast, that's unfair because you're getting all the CPU because you're typing, right? So minimizing average response time and fairness are not the same thing. So where did we get? We started with FIFO, and then we started talking about this notion of round robin, which is really literally you take the queue of the ready queue and you run the next thing and you chop it after some quantum, like 20 milliseconds, let's say, and then you pick the next one and the next one, and you process them in FIFO order, but you chop them off after a well-defined quanta. Okay, so we gave this example here. Process P1, 2, 3, 4, burst time 53, 8, 68, 24, for instance. We came up with a Gantt chart, okay, for round robin. If the quantum is 20, P1, even though it wants to run for 53, runs for 20. And then you take it off, and you put it on the tail, and now P2 gets to run. Why does it only run for 8? Because it only wants to run for 8. Okay? Just because you have a quantum of 20 doesn't mean you force the thing to compute for 20. Okay? All right, so then we go to the next one. That actually does run for 20. Okay? And so on. And if we keep going, you could figure all that out, right? And we can compute the total waiting time for each one of our processes, and this is literally the time from when you're delivered, and right now we're delivering everybody at time 0, until when you're done. That's the total, that's the time from when you were delivered to when you're done minus the time you're actually doing something useful. So it's the time you're waiting, not doing anything useful, okay? And you can average it. You can also talk about the average completion time, which is what I was just talking about, which is the time from when you showed up to when you finished. Okay? Were there any questions on this? Round robin's an easy thing, right? It's you got a FIFO queue and you just run for a while. When the timer goes off, you put it at the end, you take the next one. It's got some nice properties to it. You make sure everybody gets to run in a minimum amount of time, right? Or you can bound the amount of time they run. Obviously, as you get more and more threads, this gets less and less advantageous, because if you have 1,000 threads and you got to work 20 milliseconds through for each thread, it's going to take a long time to get there, right? So the pros and cons, it's better for short jobs, and I do say better, still not great under some circumstances, but the context switching starts adding up. So if I were to take that quantum and tune it down, it's like a knob, right? And I were to go down to 1 millisecond, or I would go down to 100 microseconds, I'm going to be switching all the time. Now this Gantt chart is not realistic. Why is it not realistic? I didn't put any overhead in here, right? So every time I go from P1 to P2 or P2 to P3, etc., I'm actually wasting time context switching. I'm saving and restoring registers. I'm changing out the address state. And so really, as the quantum gets tuned down, yeah, I'm making it through the processes quicker, but I'm wasting a lot of time in overhead. Okay? Questions on that? And I think I told you also last time, numbers that people sometimes show up is if your context switch time is, a millisecond, your quantum, you might want to be 100 milliseconds because you want to make sure your overhead is like up 1%. Okay? Or another number might be the context switch overhead's 100 microseconds. Maybe you switch every 10 milliseconds. But you want to not waste a huge amount, and they try to target somewhere between the 1 and 10% of the time as overhead. So what if we want to compare first come, first serve, or FIFO with round robin? Is round robin always better? Well, first question ought to be, here's the best first question you should ever ask somebody who says, is it better? What do you mean? Right? What does better mean? Okay? Now, the reason we went from FIFO to round robin was this problem with being blocked behind long tasks. If you got, you're in the line for milk, right? You got, unfortunately, somebody's in front of you with thousands of hamburgers, and you're trying to get a piece of, single carton of milk. Bad, right? But you put round robin in there, you don't have that problem, and so that's a reason why round robin might be better. But for instance, here's an example where all of the jobs are exactly the same. They each take 100 seconds. So we're not really talking responsiveness here, right? 100 seconds is a long time. We're probably computing. Okay? The round robin scheduler, if we have a quantum of 1 second and all the jobs start the same, you can easily come up with this table. FIFO is easy to compute, right? Or first come, first serve, because you run the first one for 100 seconds and the second one for 100 seconds and the third one for 100 seconds and so on. And what this is showing you is by the time I'm done with 10 of those, I've used up 1,000 seconds. This table for round robin with a switching time of a second, I'm not going to bother you with it. All right, that'd be kind of a waste of a lot of slides. But I'm showing you the tail end here. The tail end, we sort of at 991, we run the last second of job 1, and 992, we run the last second of job 2, and so on. They both take the same amount of time, which ought to tell you I'm not counting for overhead right now, right? But what can we say about this? Well, the average response time is really bad for the one on the right, because every job waits almost 1,000 seconds to finish. In the first case, the first one gets done in 100, right? So just because you can use round robin maybe doesn't mean you should. And in fact, if you're switching every second, that's probably okay. But if you're switching every 100 milliseconds or 10 milliseconds, your cast state's going to get in the way, and your context switch overhead's going to get in the way. All right. So, we good? Okay. So round robin, widely used, probably a default under a lot of circumstances, but not always best. Now, since I have the magic of PowerPoint, we can sort of play with this a little bit more. So, if I've got a set of jobs, I can say easily what's the best first come, first serve processing order, where what best in this instance means I'm optimizing for average wait time and average completion time. And what we know is if I happen to rearrange things so the short job is first and the next shortest is second and so on and so forth, that's going to optimize the total completion, the total average completion time for these guys. Okay? And so the best first come, first serve, for instance, comes up here as an example where the average wait time is 31.5. So notice P2's got it has a wait time of 0 because it starts right away. Is everybody with me on this? And so we can lay this out and we can figure out that the average wait time is 31.25. But if we do the worst first come, first serve, which is what? Well, you put the longest one first and you work your way through. The average wait time there is 83.5. So you see there's a big difference in average wait times just by rearranging. Okay? So, and same with completion time, right? So the average completion time is 69.5 here. It's 121.75 there. All right, now, what about round robin? Well, if we have a quantum of 8, for instance, and we do this switching, and you guys can all do this now. You could sit down with some graph paper and write out what the scheduling looks like. What you'd find is if the quantum's 8, my average wait time is 57.25, and my average completion time is 95.5. And should it surprise any of you that it's between the best and the worst first come, first serve time? Probably not, right? You're probably not totally surprised by that result. But what you can see is if I go and try some other quantums, it's not quite so clean, okay? Because it's about boundaries and where things come into play. And the bottom line here is that round robin gives me middle-ish behavior that doesn't succumb to being the convoy effect of being stuck behind the long guy. Okay. Isn't that fun? All these great colors, magenta, okay, cyan, green. Do we have any questions on this slide before I move on? Good. Now, of course, we haven't talked about overhead in any of this, right? So, obviously the round robin starts having problems with overhead, and obviously the cases where the quantums are smaller, the overhead dominates more than when they're bigger. Okay, I'm going to move on. So the other thing to note, same table, but let's look at columns instead. What you see here is that the short task, which is P2, really gets jerked around a lot as I change my scheduling. Okay? So as I change the scheduling, that poor little short task, which might be you trying to type your sonnets, which you all do at night. I know you're typing them into your computer, to be or not to be. That's the question. How do I love thee? Let me count the ways. But what you see is those short things, those short tasks really do get moved around based on scheduling. And the other thing to note is the long ones, they don't really care based on scheduling, right? So this kind of tells you something like, well, maybe if we gave some preference to the short ones, we could get more responsiveness without really interrupting the long ones. Okay, that's the lesson from that. Good? Okay. All right. Now, the other thing, in addition to a bunch of tasks that are all sort of co-equals, is priority. All right? And the notion of a priority scheduler really is another axis. It's like something you can do in addition to everything we've been talking about. And that is you give priorities to different tasks and you run things in priority order. So the execution plan here is that you take the highest priority that's runnable, and those are the jobs that run. So a pure priority-based scheduler like this would run all the priority 3 things, job 1, 2, and 3, until they're all gone, and then it would do priority 2. Okay? So in a pure priority scheduler, really the low priorities don't get to run at all as long as there's higher priorities. Right? What are some problems with this? Well, an obvious problem is starvation, right? Because if you always have high priority things come into play, it's possible that the low priority ones never run. Okay? There's a fun urban legend that was running around for a while about Multics. The Multics scheduler at MIT, when they shut it down, they found a job that had been sitting there for 10 years. Now, we know that's not true. But where do urban legends like that come from? Well, because priority scheduling has a serious starvation problem. Okay? The other interesting thing is priority inversion. So priority inversion is a good example where priority 0 task, say job 5, grabs a lock, and then a high priority task comes in, and it preempts job 5, and the high priority starts running, except that then it tries to grab the lock. Okay? So now you got a high priority one trying to grab the lock, a low priority one has the lock, and then somebody in the middle shows up and they just run. Okay? They compute pi to the last digit. There's a bad scenario where the high priority guy never gets to run, called priority inversion. We'll talk more about this, but this actually impacted the Mars rover at one point, where the high priority thing was bus communication, the low priority thing was a source on the bus, and something in the middle was basically trying to do a regular task. Those 3 together give you this weird priority inversion that's a problem. All right? And the way you fix this is you no longer do pure priority-based things. And the one way to think about priority inversion, by the way, is priority inversion is it's a breaking of the intent of the priorities, right? The intent of somebody who assigned priorities was, I want my high priority thing to run over everybody else. Except what I've just described as a scenario for you, that high priority one is stuck. It's not running, right? So we have violated the intent of the scheduler and policies set by the user because of the priority inversion. And so what do? Well, you start dynamically adapting your priorities. The simple fix for this is something called priority donation, where the high priority guy who's blocked hands over some of his priority to the low priority guy so he gets to run long enough to release the lock, and we're all happy. So dynamic priority in there can be very important. All right? Questions? Now, every scheduler you're likely to use has a priority component to it, which begs the question, how the heck do you set the priorities? What's a high priority thing? What's a low priority thing? That's policy, and anybody who's had to sit down and actually come up with priorities finds that invariably it's tricky at best, okay, to really figure out what the right priorities are. And so what happens? Dynamic priority adaptation, where priorities get changed based on somebody trying to estimate something. We'll talk about that in a moment. That kind of doomed the O1 scheduler in Linux. So let's go back to fairness now. So do we have any other questions on priority? I think the great thing about priority is, again, it's an orthogonal axis to like round robin or FIFO. When I'm running priority 3, there's nothing that says that jobs 1, 2, and 3 can't be done round robin or FIFO or any other scheduling policy you want. So it's an orthogonal axis, but it becomes a difficult axis, like I said, to assign. Okay, so what about fairness? Okay, and again, this sounds like a philosophy class. What is fair? How many people think fair is this? How many people think fair is that? We could be watching the Democratic debate right now, I suppose. But a strict fixed priority, which is going on, but I have TiVo recording it. But anyway, so a strict fixed priority scheduling between queues is unfair. Okay, why? Because the highest priority thing just plain gets the CPU, right? And as a result, long-running jobs may never get the CPU, and there's this urban legend about Multics. You got to give long-running jobs a fraction of the CPU, even when there are shorter jobs to run. So maybe to get fairness back into a priority picture, you start saying, well, yes, we're going to give priority, the high priority ones, most of the CPU, but we'll occasionally give a little bit, throw some crumbs. to the low priority ones, right? And so the trade-off is almost invariably that fairness gained by hurting average response time, fairness gained by violating the priorities also. Okay? So how do you implement fairness? Well, you could give each queue some fraction of the CPU. So we're looking at the priorities now. So the high priority one gets 80% of the CPU. The next one gets a little bit less. And then you start asking questions like this. Well, what if one long-running job and 100 short-running ones? Okay, so what fraction? Let's see. I want to do a fraction. So this is an interesting, complicated problem. So that the net effect is 10%. Right? So this gets messy, right? As you start adding more jobs in there, then do you adjust what fraction the priority queues get? And you could increase priority of jobs that aren't correctly running, I suppose. This guy was really low priority, but he didn't get to run, so I'm going to slowly raise his priority until he gets to run a bit. Okay? And when the system gets really overloaded, no job gets the CPU, so maybe we actually swap a whole jobs out. We're going to talk about that a little later in the term and start something to try to make some forward progress. So what's the point I'm making here? The point is, well, you got some simple, pure things like a priority scheduler and FIFO, but they're not perfect, and so now I'm going to put heuristics in, and I'm going to start adjusting my priorities dynamically based on some very complicated heuristics that try to figure out that job hasn't been running, but it should because it's really interactive, because I sort of figured out that it was interactive by observing it for a while. You think I'm making this up, but there's a lot of schedulers that have volumes of code whose job is to have these heuristics, try to figure out how to dynamically adapt priorities and scheduling quanta based on what they think the job is, okay? And you can imagine if you're an operating system scheduler designer, you start going nuts trying to figure this out. And worse, you got customers who are used to the old way, and so you can't change the scheduler. So anything you add has to basically look backward compatible, but you add a few other things. So, all right. So let's try something a little different. Let's try lottery scheduling. I don't know why our little guy here with the lottery is off to the edge there, but lottery scheduling is an alternative to try to avoid these complicated heuristics. And so the idea is you give every job some number of lottery tickets, and every time slice you draw a random lottery ticket, and the job whose lottery ticket you just drew gets to run. Okay? And then his time quanta go up. You draw a lottery ticket, and somebody else gets to run, and then her time quanta comes up. And so this idea now is what I do to adjust the fraction of the CPU is I give more or less lottery tickets. Okay? And it dynamically adjusts, and assuming I never give 0 lottery tickets, what I can guarantee with this, for instance, is that some job always runs. Okay? But on average, the CPU time is somehow proportionate to the number of tickets. Okay? And how do you assign tickets? Oh, I'm talking about shortest real-time first, or shortest runtime first. I haven't talked about that. Give me a couple of slides. But basically, to avoid starvation, every job gets at least 1 ticket. The advantage here over strict priority scheduling is it behaves very gracefully as the load changes. So as you add more jobs and you start redistributing the tickets, kind of everybody gracefully degrades, and they get slower, but there's nobody that's totally locked out. Okay? So here's an example. Here's some examples. So we can imagine that short jobs get 10 tickets and long jobs get 1 ticket. Could somebody give me why that policy makes some sense? Yes?
The long jobs are going to hit that ticket and then run for their duration, where long tasks only need to run, for a shorter time more often.
Okay, good. And why give them more tickets? And? Yes. So the idea is shorter burst time, more priority because we care about interactive. So the way you get more priority in the lottery schedulers, you give them more tickets, right? So the short jobs, we're going to give more tickets. The long jobs, we're going to give 1. And a good example of that is here, where we have 1 short job and 1 long job, and the short job gets 91% of the CPU, and the long job gets 9% of the CPU. And that might be a perfectly good policy if what we wanted to do is make sure that we got interactive behavior, so the person with the short jobs that is typing isn't annoyed, right? And then you can look at a bunch of different options, like if you have no short jobs but two long jobs, they each get 50%, and vice versa, 50%. If you have 10 short jobs and one long job, you kind of get 9.9% and 0.99%, et cetera. You can work out this table on your own. The bottom line is this graceful degradation, because if I start from a point here with 1 and 1, and I start adding short jobs, the CPU kind of cleanly redistributes over the short jobs, and I don't get any cliffs where suddenly nobody runs. Okay? All right, and you can start saying, what if there's too many short jobs to give a reasonable response time? If the load average is 100, it's kind of hard to make progress no matter what. So at some point, if you put too many threads into the system, nobody makes progress in a way that anybody's happy. Okay, so of course, these scheduling policies we're talking about can't make up for trying to get too many things running simultaneously. What do you do at some point? You buy a new computer, right? Some point you're trying to run so much stuff, you get a bigger CPU with more cores and whatever, okay? All right, questions? Yes? How do you know what's a short job and what's a long job? Magic. That's a very fair question. In fact, we'll talk about this in a moment, but you need to predict the future. Okay? And boy, if you'd predicted the future, you would have sold all your stock before the last 2 days of the market, where it's down 1,900. There's a second question back there. Go ahead. I like that question. So how is it that the scheduling algorithm gets to run? Right? I mean, it'd be funny if the scheduling algorithm was too low priority and never got to run, right? That would seem like you're in trouble. So the bottom line is the scheduler gets invoked when the quantum expires. The timer goes off. You take the current thing that's running, you put it on the end of the ready queue, whatever, and at that point you run the scheduler to pick the next thread. So the scheduler, to say that the scheduler is running at the absolute highest priority is a little bit weird because the scheduler gives the priority, but you could say that it gets every arc where you change a job, the scheduler gets to run. Okay? Does that answer your question? Question here, yeah. So getting a certain so this is a mapping between how tickets give you a fraction of the CPU. Let's answer the other question that was kind of buried in that. What does it mean to get 90% of the CPU versus 10%? If you imagine that, remember that diagram I showed you the first day where we sort of had thread 1, then thread 2, then thread 1, and then thread 2, and we kind of switched between them? So what 90-10 would mean is that thread 1 gets 90 and thread 2 gets 10 as you add it all up. So it's what fraction of the total cycles are given. Okay, good. Other questions? Yeah. How do you measure CPU burst time? Once again, predict the future. So the burst time is how long am I going to run until I stop because of an I/O operation. So burst time, shortness of jobs, these are all about predicting the future. Well, it's between, it's from the point that you start running on the CPU till you do something that's going to reschedule you. And a good example would be you do I/O. Or you do, like, you go to sleep waiting for a key press. Or you yield. Any of those things would be the end of the burst. Now, just in case you guys think I'm being facetious, when I say you got to predict the future, I'm going to talk about that in a moment, okay? I won't tell you how to make money in the market, but I will tell you about what the notion of predicting the future is in a second, okay? Question back there, yeah. By jobs, do I mean threads or processes? Yes. So the funny thing is, I'm giving you a policy here about scheduling things. There's a meta policy about are the things I'm scheduling processes or are they threads? Are they all the things owned by one user, etc.? So you could use lottery scheduling in different ways. You could use it to schedule threads. You could use it to schedule processes. You could use lottery scheduling, for instance, to schedule processes, and then during that time quanta, you do round robin between all the threads. Okay? Maybe that's a good thing. Maybe it's not. Yes?
Part of the, I guess, sort of intro to this was that it would reduce the amount of heuristics that you have to tack on, but it seems like it's, I mean, is that really easier to predict the length of the jobs than to try to assign?
Well, I'd say they're both equally hard in terms of shortness versus priority choice, because usually when you're assigning the priorities, you're trying to figure out how long it was. So these are all related to each other. The question here is, are the mechanisms, once you've figured out what your burst time are, is it easier to figure out what the right thing to do is? And I would argue that this is sort of related to fair queuing. How many people have run into fair queuing in like 168, or anybody in the networking classes here? The basic idea there is that I'm going to try to give, on average, a fraction of the CPU to each job. So lottery scheduling is a way to do that cleanly. Okay? Whereas priorities, what does it mean? If I make high priority, I'm essentially giving all of the CPU to something unless I do some weird heuristic. All right, good. Any other questions? Now, in addition to showing you different ways of scheduling, I'm hoping that I'm giving you this notion that scheduling is an art, not a slam dunk, okay? People will claim that they know the best way to schedule. They're either confused or maybe they're trying to pull one over on you, okay? So scheduling is policy, scheduling is heuristics. The question is, can I get a heuristic free or a less heuristic world where things behave in a way that's more predictable? That's a goal. Okay. Now, how do we evaluate a scheduling algorithm? So I've got the scheduling algorithm. I've got a bunch of jobs. How do I evaluate this? Well, one thing is I could take a workload and compute the performance of the algorithm on the workload by doing some, analysis tools and coming up with a number which says, on average, this thing meets my, I get better average completion time or something by running this model. That's really hard to do, okay? Because basically, this is worse than trying to actually run the thing. The other thing you could try to do is build some queuing model that has a lot less details to it and tries to come up with how well the scheduling algorithm works. Sometimes that works, but queuing models are also very complicated. Really, what people do is they simulate something simple, which is they have a workload that represents transitions, number of threads, and how long they run, and burst times, whatever, and they feed that into the simulator, and the simulator kind of looks at the transitions and pretends to be a scheduler on a real machine, and maybe you can get some idea what the actual average time might be. Okay, and this might actually be less complex than running the whole thing. But it's actually pretty hard to evaluate as well, because obviously what you'd like to do is try 12 different algorithms. I'm showing first come, first serve, and several others here, round robin, and then pick the best one for a given workload. That would be the ideal. But you could find many papers in the literature where people have tried to come up with one of these evaluation models to prove that their scheduling algorithm is best. Sometimes you believe them, okay? But ultimately, the kind of machines you guys are using now, you got laptops, you got phones, they really have a mix of interactive and high throughput applications. And the question might be, how do you best schedule them? And how do you recognize one from the other? Now we're getting into that predicting the future question, right? And if you say, ask the app, are you interactive? And it says yes. Do you trust that? Okay, I don't know. What if the developer knows exactly how their app works? How many of you guys have ever ran some code and you knew exactly how long it was going to run? Nobody? Bueller? So, yeah. So even a non-malicious app writer doesn't always know how their apps actually behave because code's complicated, right? And the other question that's interesting is, does the same scheduling heuristics make sense on clouds and phones? Probably not, because the mix of usage is a little different, right? In the cloud, you got these big jobs that run for a long time. In the phone, you got these short interactive jobs. So maybe you're actually going to run a different scheduler on those environments, okay? So for instance, is observed burst time useful to decide which application gets CPU time? Short bursts means interactivity, maybe high priority. Okay, let's talk about predicting the future here. If I have a job and I watch it, by the way, I'm using job to mean either thread or process or whatever you want to talk about. If I observe it and every time it runs, its average burst time in the past was short, I'm going to predict that its average burst time when it just showed up is short. If it typically runs for a very long time, I'm going to predict that its next burst time is long. Okay. Notice that what we're doing there is we're predicting the future based on some notion, not always accurate, but often, that it's going to have similar behavior to what it did in the past. There's where we're getting into predicting the future, right? If I see a lot of really short bursts out of this job, probably we're going to have short bursts going forward. And many schedulers have that assumption encoded. So apps that sleep a lot and have short bursts are probably interactive apps. Okay, so I'm observing it. They have short bursts. They sleep a long time. They're probably interactive. Apps that compute a lot maybe should get lower priority because they look like they're not interactive. Okay? Now, of course, I'm making some value judgments here that interactive is more important than compute. That may be great on your cell phone. Maybe it's not so good in the cloud. Okay, so we got to decide what environment we are. But ultimately, it's very hard to characterize apps. You know, what about apps that sleep for a long time but then compute for a long time? I don't know. What's that? Okay, or what about that's Alexa, right? He sleeps for a long time. Oh wait, no, Alexa's listening all the time. Okay, or what about apps that must run under all circumstances? Say periodically. That's a completely different animal. So that might be a real-time thing, which we haven't talked about yet. All right. So any questions before I do some administrivia? So, big surprise. Thursday is the 27th. Oh, wait. There's a midterm on Thursday. All material up to today's scheduling, since we've mostly talked about it. You get one sheet of handwritten notes, both sides. Okay? If you can write it, you can have it on your sheet. Now, what we don't want is no microfiche. Actually, you guys don't even know what microfiche is anymore, so I don't even have to tell you that. But you can't take the complete textbook, microfiche it, print it on a piece of paper, and bring a magnifying glass. That's just not allowed, okay? Now, one thing I didn't put on this, which I should have, is we are going to give you a function signature cheat sheet, which has a bunch of, functions you're likely to run into that you've encountered during the course of this term so far, and what their arguments are. We'll give you that. Okay. In fact, we may even release that on Piazza in the next day or so, just so you can see what it is. But you don't need to write every function you can come up with. You don't have to put it on your sheet. Okay. Save your sheet for other things. Okay. Now, we won't necessarily tell you what the function does, but hopefully you know it well enough to know it by name. Okay. All right. Tonight, we have a review session. Okay, so you get a big break after class. Okay, maybe you don't. So it's from 6:30 to 8. Sorry, that was when the room was available. And be here. I'm sure it'll be very, very exciting and much better than my lecture, so I highly recommend it. And then as far as room assignments, so watch Piazza in the next day. We'll tell you where to go. There's 5 rooms, and we're going to have some letter, if your last name is between, A and F or whatever, you go to one room and so on. We'll have that out for you. Okay, so watch that. Okay, any other questions about this? Yes? So they include what? If you should be interacting with us, you are interacting with us, and no. So that's a via email thing. Okay, any other questions? Good. Okay. Don't need a calculator. Bring your brain. That you'll need. Probably want some water. Okay. So what if we knew the future? So could we always mirror the best first come, first serve? So that would be, if we knew the future, could we rearrange the jobs so we somehow got the best parameters? And the answer is yes. Okay, if we knew the future, okay, shortest job first, run whatever job has the least amount of computation to do, and pick that one. So if you knew in advance what had the shortest amount of computation, then you'd run the short job first, the next shortest next, and so on, and you get the best parameters out of that. Best average wait time, best average completion time. Okay. Now there is a slightly different, more powerful version of this called shortest remaining time first. All right. And this is a preemptive version of SJF, and what it says is, if a new job arrives that has a shorter time, you just stop the one that's running and you run the shorter one. Okay, so that's pretty much what we normally think of, okay? Or sometimes shortest remaining time to completion first, or if a new job comes in that has a shorter burst time than the one that we're currently running, run it. Okay? Question on that? Now, of course, this is if we know the future. Okay? And you can apply this to the whole program or the current CPU burst. And the idea is to try to get all the short jobs out of the system as quickly as you can, making those interactive folks happy. And the big effect is on short jobs. And, of course, as we saw earlier, it's only a small effect on the long jobs. They mostly don't care unless you totally lock them out, and then they totally care, right? But you're going to go after better average response time. Now, can anybody think about what might be an issue with either of these? Let's say SRTF. Yes. Yeah. If you have lots of short jobs, the long ones don't run. Game over, right? Because you keep running the short ones. So, what do we call that? Starvation. So this has got a starvation problem, right? If you really know the future, and if you've got lots of short jobs, you might have a problem. Now, SJF or SRTF are the best you can do at minimizing average response time. Okay? It's provably optimal. Right? SJF among non-preemptive and the SRTF among the preemptive ones. And since SRTF is always at least as good as SJF, we're just going to talk about SRTF. How do you compare SRTF with FCFS? Well, if all the jobs are the same length, how do these two behave? If jobs are exactly equal length, what's the difference between SRTF and FCFS? Anybody? Yes. Nothing. Why? Okay. Now, correct. They're going to schedule things exactly the same way if they're all the same length. But let's talk this through for a second. FIFO's easy, right? You have all the same length, and it just runs the first one, the second one, the third one, the fourth one, the fifth one. Hopefully, that's not too confusing. But what about SRTF? If they're all the same length, you start running the first one, and as soon as it runs a little bit, it's now shorter than all the other ones. So it's going to run to completion. Right? The moment you start running the first one, it gets short, and it now runs to completion, and then you pick the next one. Okay? So that's why these two are the same, because SRTF notices the job is now shorter because it's run for a little bit, and it just runs it to completion. Okay? Does that make sense to everybody? Not. Give me a question. All right. So SRTF becomes the same. What if the jobs have varying lengths? Well, SRTF is going to make sure that short jobs are not stuck behind the long ones. Or, remember the convoy effect we talked about last time, where you got a big one and a bunch of short ones, and the short ones are basically out of luck? SRTF will take a queue that's got a big one and a bunch of short ones, and it'll immediately pull the short ones in front and run them. Okay? That's what it does, because it's preemptive. Okay? All right, question. Anybody? Good? Now, these are just words, so let's see if we can talk it through a little bit. And by the way, I still haven't really told you how to predict the future. We're assuming we've got a good prediction of the future. Now, what's unfortunate about me blowing up the screen like this is it's doing something funny with PowerPoint, but that picture of that woman that I had earlier is actually looking at a crystal ball, so you have to imagine that. There's a crystal ball there that's cut off for reasons I'm not sure I can figure it out, okay? So we're assuming that we can predict the future. So let's assume the following. We have 3 jobs, A, B, and C. A and B are CPU bound and they run for a week. That's a long time, okay? C is uses 90% of the disk, and then and the other sort of 10% is compute. So it computes for a little while, it runs, does I/O for a long time, then it computes and it does I/O. So this job, C, you could think of kind of like, I don't know, you're copying a CD, you know, you're ripping a disk, or it's doing some thing that has a little bit of compute and a lot of I/O, and the way to get the best behavior out of it is to make sure that it always gets 90% of the disk, because the disk is a really slow thing. And so I want to make sure that I don't waste time on the disk. I want to get it running as soon as it can, because it's going to take a long time. So the way to make C work well is to keep this 90%, 90-10 function where 10% CPU, 90% disk, okay? Now we're going to throw all these together, and you can immediately imagine what goes on. Well, with first come, first serve, once A or B gets in, it runs for a week. I'll tell you that disk stopped, okay? Because C is no longer running, right? So first come, first serve is just bad idea here, okay? Everybody with me on that? Just a bad idea. But what about round robin or SRTF? Well, let's look at this a little more carefully. So, for instance, here's SRTF with round robin at 100 milliseconds. So what happens, for instance, is C runs until it hits I/O, and then it stops because it can't run anymore. So then A gets to take over. So we know that C is going to run for a short period of time. Then A gets to run for 100 milliseconds, and then B gets to run for 100 milliseconds, and then C gets to run for a short time. Okay? So are we going to get our maximum disk utilization out of this or not? How many people think we're going to get good disk utilization? Okay, how many think we're going to get bad disk utilization? Okay? How many people don't know? Okay, so let's see if we can compute this. The disk utilization is 9 out of 201. Okay, we get about 4.5%. Okay, because we got 100 milliseconds here, we got 1 millisecond, and so we run 9 milliseconds for every 201 milliseconds, so we got 4.5% disk. Not very good. Okay? So can we do better? Yeah, we could have round robin with a millisecond. And so now we keep switching. We do C, A, B, 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 C, A, B, A, B, A, B, A, B. Now you might ask yourself, why does C not run all the time? Can somebody tell me why it's C, a bunch of A, Bs, and then C eventually? Why does C not run? Why are we not doing A, B, C, A, B, C, A, B, C? Go for it in the back. Yes, C is on a wait queue. Okay, you got to keep this in mind, right? C runs for a millisecond. It launches the I/O, then it goes on the disk wait queue for another 9 milliseconds. It can't do anything, right? So that's why A and B alternate. But eventually the disk comes back, C gets back on the run queue, and now we do C again, A, B, 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 C. So how is this? Well, we have just approximated good disk utilization, but we're switching a lot. Okay, and we're wasting a lot of overhead. Okay, so this is better, but probably not great, because we lost all of what's bad about this. Well, a lot of overhead. What else is bad about A and B switching frequently, other than just overhead? Yes? Cache state, right? Our cache state screwed up. So we're not actually allowing the processor to get fully up to speed with its pipeline and its cache because we're switching a lot. Okay? So SRTF looks like this. C runs for a millisecond, and then A I'm just picking A, starts running. As soon as A starts running, A is now shorter than B for its remaining time, right? Just because it's run for a little bit. And so what that means is C is clearly the shortest thing, then A runs for a little bit, and then C comes back on the ready queue. It's clearly the shortest thing. It runs for a little bit, and then A takes over, etc. No B in this. Why? Because B is now the longest element in the system because A has started to run. Okay, and this, by the way, is 90% disk utilization, and A is going to get to run with its best cache state and pipeline state that it can, given that we have to run C every now and then. Okay, questions? Yes? How the disk utilization got calculated? Yes. So to do that, let me just go back to this. That's a good question. If you look at what makes this work well, okay, it works well because we do a millisecond of compute, and then we ask for I.O., and then the disk runs for 9 milliseconds. Okay, now, those are just numbers. I've got them right here that I'm going to say is what happens with C. And if you compute that, what you see is that the disk runs 9 milliseconds out of every 10, so it's 90% utilized. You with me so far? And so when we go down here, what we see is the following. So C has got a millisecond to run. It's clearly shorter than A and B, which are weeks or a week long, right? So C runs for its millisecond. It launches its I.O., and then A starts running. Dun, 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 dun. And then eventually, 9 milliseconds later, the I.O. comes back, and C gets put back on the ready queue, and then it gets to run again. And so what you see is that the disk is operating 9 milliseconds out of every 10. So we're perfectly at 90. Got me? Good? Yes, in the back.
Yeah, so if you have like an I/O device, like for example,
So if it's worth its salt and it knows that it's a gaming console and it knows something about it, it's going to try to do that. So the slow things in the system, like I/O, are things you're trying to optimize for. Well, there's a lot of stuff that you as a user don't get to see that's sort of statistics that are inside the system. Okay? So I'm not going to tell you that your gaming console necessarily does this, but what it's going to try to do is it's going to try to make sure that things that are very important for either responsiveness or for good use of I/O are going to actually get to run frequently enough to optimize for the I/O. Okay? And another way to put this is optimally we want to overlap at least compute and I/O, because I/O is long-running, compute's long-running. We want to make sure the two of them do a good job of overlapping, because then we're maximally using both resources well. And what I'm indicating with these slides is that actually can be a scheduling issue to schedule it properly. And of course, there are several things that are wrong with this slide, right? First of all, I don't know for sure exactly how long any of this stuff takes, so there's clearly some prediction in here, right? And the second thing is, of course, SRTF's got to predict the future, so there's clearly prediction in here. The other part is that this I/O operation is unlikely to be exactly what I just said, so figuring out how to exactly run it to exactly optimize the I/O is not always going to work properly. Good. Any other questions? Yes? For remaining time, do we mean the time for the process to exit or the time to yield? What I'm using here is the time until the burst is up. So I'm assuming these things, for instance, are running for a week or whatever. So I'm assuming we're not talking about exiting. We're talking about the time until it does its next I/O or something that's going to require it to give up the CPU. So burst time is the model in your brain you should have. We're talking about burst time here. So it's the remaining time until burst time. Good. Any other questions? Good. All right. Good questions. So, starvation is unfortunately here, right? So SRTF clearly leads to starvation if there's lots of small jobs and large ones never get to run. Somehow we need to predict the future. Okay, how do we do this? Some systems might ask the user The programmer says, well, when I run, I have a burst time of exactly 100 milliseconds. No. All right? We know that users don't do a good job, but you could say, well, in order to stop cheating, what's going to happen is if they're wrong, we're going to kill their job. Well, maybe that's okay if you actually have people cheating, but what you've just done is you've killed off jobs that any normal programmer writes because they can't figure out exactly how long things take, right? So asking the programmer to somehow predict things is really just not in the cards here. The bottom line is you can't really know how long a job will take. However, we can use SRTF as a yardstick for measuring other things. So think about SRTF as a guaranteed not to exceed policy that we're going to measure against. And it could be something that we're going to try to approximate to, and I'm going to tell you about that in just a second, about how could we get close to SRTF such that we're sort of like we're predicting enough of the future that we could get SRTF behavior. But think of SRTF as the guaranteed not to exceed optimal case against which we're measuring. So the pros and cons, it's optimal. And for average response time, unfortunately, negatives are it's hard to predict the future and it's unfair. All right, let's take a break, come back, and we'll continue. So let's continue. So, how do we predict the future? So, basically, what we want to do is we want to build some adaptive policies based on past behavior. The assumption on many things, so if you look at caching, you look at when we start talking about virtual memory, paging, we talk about a lot of things. The prediction or the notion is that things are going to behave in the future similar to the way they do in the past. And that's really because programs have predictable behavior. And so an example might be, well, if SRTF, you have an estimated burst length, you could build an estimator function. Like here, you could do exponential averaging of all of the last bursts and come up with an average. And you have this tuning parameter alpha in the simple case that sort of says how much is the current estimate versus the previous one, what's the weighting, right? Or I'm sure some of you have taken classes that talk about Kalman filters, right? There are lots of ways that you could do this. I guess what would be a modern thing to think about is machine learning, right? You could do machine learning on the burst lengths. The question is, what's the trade-off between how long your scheduler has to run to pick the next task versus running the task? So there's obviously a diminishing return at how accurate things are, but nothing is kind of out of the picture, but I do want to point out that this exponential averaging is really simple and works really well. And I'm sure you've run into it in the past, okay? Another possibility, so there we're actually building a model of the burst size based on two past measurements. Here's another idea which is very common in a lot of operating systems, which is called the multi-level feedback scheduler. And what we've got is, rather than one queue, why not have many queues, okay? If a little bit's good, a lot's better, all right? And so the idea of this is we have each of these queues has a different quantum or even a different scheduling policy. So this is round robin with 8, round robin with 16, FIFO. And the idea is that if you run long enough to expire your quantum, you get shoved into the next lowest queue. Okay, so if you run for a long time and you run for 9 units of time, you get pushed into the next queue. And then if you run for 17 or more, you get pushed into the next queue. All right? And so this is actually a very old idea from way back when. Many queues, different priority. The ones at the top have the highest priority. The ones at the bottom have the lower ones. Each queue has its own scheduling algorithm. And the idea would be that you go up whenever you sort of run quickly. So if you're running here with a quantum of 16 and you end in a millisecond, you get promoted. But otherwise, if you're using too much CPU, you get demoted. Okay? And so essentially, you could say we're adjusting each job's priority based on its behavior. This is a type of prediction of the future because things that have short burst lengths tend to stay high and things that have long burst lengths tend to go down in the queue. And as a result, if you have high priorities in the top queue and low priorities in the low queue, you get SRTF-like behavior, right? Because the things that are short run frequently with high priority and things that are long run down below with low priority. Okay? And many operating systems have operated in the past with many levels like this. Okay? And so the results are kind of an SRTF approximation. CPU-bound jobs drop like a rock and short ones rise up. There's some interesting questions here, though. How do you schedule between these queues? So if you have only fixed priority scheduling where the top thing is the highest priority and the lower ones are lower priority, that could be a problem because you could end up with starvation again of the low priority things, right? The other is you could give a time slice where you say, well, yes, we have highest priority at the top, but we always give a few cycles to the low one so we make sure everybody gets to run. Okay? Now, a lot of operating systems, several of the early BSDs, Sun Microsystems, Sun OS, a bunch of the early ones had 16-level queue things like this with different heuristics for when you go up and down. And based on where you are, you get more or less CPU. Okay? And so you can go crazy if you want. You could do all sorts of heuristics, not just this simple going down. You can make much more complicated things. And so an interesting thing about this, though, is if you know that this is operating, your scheduler's operating this way, you could start being malicious and put countermeasures in, right? So, for instance, what's a user action that can foil the intent of the OS designer? Well, for multi-level feedback, you put in a bunch of meaningless I/O. Printf, printf, printf. What does that do? Gives you a short burst length, and you rise up and get more CPU. Okay? So all the downtrodden tasks at the low part rise up, okay, to get more CPU. There is an interesting example. One of the first examples of people playing computer games against each other was an Othello contest many moons ago, where one of the contestants figured out that by putting a bunch of fake I/O into their Othello program, they could actually cause themselves to get higher priority, and so they actually got more priority, more compute time, and did better. Okay? So this is interesting, right? As the heuristics get more complicated, so do the malicious exploitations get more complicated. Now, let's talk about the O1 scheduler. So in the old days of Linux, early 2000s, there was this big innovation called the O1 scheduler. What is the order 1 notation talking about? It's talking about the cost of scheduling relative to the number of threads. So in theory, with an O1 scheduler, doesn't matter if you got 100 threads or 100,000 threads, it's order 1 scheduling time. Sounds good, right? And in fact, it was pretty good, but let me talk you through this for a moment. There were actually 140 priorities. I've got them labeled from 0 on up to 139. And all of the ones between 0 and 99 were called real-time priorities. And if you put a task in those priorities, which you as a user, not a super user, couldn't actually do. You had to be super user to do this. But if you did that, you got strict priority scheduling out of it. And you could, they're called real-time because you'd get very predictable behavior. The 40 up here are the ones that you as a user would normally see. And as you raised your niceness level up, things would run with lower priority. And as you lowered your niceness level, they would get slightly higher priority. And so this is the way nice worked. Okay? And this was O1, right? So now, the way they did this is they actually had 2 scheduling queues. So this is really 140 scheduling queues up there, right? So they had 2 sets of 140. And the idea would be that they had the active one and the expired one. And as you were running and scheduling, as soon as your time quantum expired, you get put over into the expired one. And when there were no tasks left, you'd swap them. And that was kind of, I don't want to go in this right now, but that was part of how they got the O1 scheduling, because they had a way of basically only computing your next time quantum when you went from done to the next, over to the expired level. And so you're basically, wasn't complicated. And the reason this was a really big deal was the previous scheduler, I think, had ON. Okay, and so it's very complicated. It started getting very expensive as you added more threads. Now, we did talk about this. The last thing I wanted to say is the time slice depended on priority here. So things with higher priority, which is to the left in this diagram, got more time slice than things with lower priority to the right, which kind of makes sense, right? Priority more important. You get to run with higher priority, more quantum. And then once you had that, you ran round robin in a single priority. So this, of course, was for Linux. Well, Linux is an operating system you're all well aware of that basically ran both interactive and computational jobs. And so what did you do? Well, you took what I did. This is relatively straightforward. I realize I just went through it really quickly, but basically we have a priority scheduling queue with some things to try to make it fast. Hopefully that's not too complicated, but it doesn't really necessarily tell you how to make interactive jobs behave interactively in a clean way. And so what did they do? They put heuristics on top. Okay, so this is where O1 started getting dicey. Okay, so the idea was there's a user task priority adjusted plus or minus 5 based on heuristics. So if you slept for a long time, it raised your priority, and if you ran for a long time, it lowered your priority. And there was this thing called interactive credit, which was gained when you slept for a long time and spent when you ran for a long time. And the interactive credit was used to help raise your priority or lower your priority, so that somehow, when this all worked out, the interactive ones got to run with higher priority, and the computational ones got to run with lower priority, and hopefully everybody was happy. Okay? And then the real-time tasks always worked as strict priorities, so that was fine. Well, as you can see, this got really complicated really quickly. So it started pretty soon. You start putting all these heuristics in there, and then the system, you give it a bunch of jobs, and you're trying to run it, and you don't know why it's scheduling the way it is. I mean, why is that job going up a little bit? Well, it's getting some interactive credit. So this got pretty bad, okay? It was very low overhead scheduling, but its behavior was hard to predict. And so that led to the CFS scheduler. And you guys should Google this, because there were some good blogs on this. Basically, The 01 scheduler was supposed to save the world, and it got so complicated nobody could understand it. And so, as you could imagine in the Linux community, there was a lot of very strong personalities involved. And somebody says, let's do something different. Let's do this new scheduler, which first appeared in the 2.6.23 kernel. And it basically says, well, let's forget all these heuristics. So CFS doesn't track sleeping time, doesn't use heuristics. It just makes sure that every process gets a fair share of the CPU. Okay, now, anything that says we're going to get a fair share of the CPU, hopefully the beginning of this lecture makes you a little suspicious of anything that says, right? Okay, but let's see where we go with this, right? So this is definitely inspired by fair queuing. And so the idea is that every process gets their fair share of resources in a fair queuing standpoint, which, by the way, is a well-defined idea. And it models an ideal processor. So the idea is when you run, you use up virtual time in an ideal processor world. And when you don't run, other people use up virtual time. And so if you look at everybody who's run and you say, well, he got to run this amount of time, he got to run this amount of time, the one that's got to run the least gets to go. So we're trying to be fair. We're trying to make sure everybody gets to run a fair amount of the CPU. Okay, and the way you get priorities is if you take a certain amount of real time that you run and you divide that real time by 2, that means the virtual time goes half as fast as other people's virtual time because I'm divided by 2, which means that I ultimately get twice as much CPU because my little bit of real time isn't as much virtual time. So trying to keep all the virtual times the same, I get to run twice as fast. Or twice as much. So by basically adjusting these weights, I basically set who matters from a priority standpoint, and then they get completely fair queuing because we just keep these virtual times the same. And this is actually, if you were to think about this, this has got a lot of similarities to the way that the lottery scheduler worked. Okay, they're both related to kind of this fair queuing idea. And the other thing in here is if you take all the tasks that are running and you weight them properly, there's this thing called targeted latency, which makes sure that everybody gets to run. And there's some really cool hacks in here that basically use red-black trees to make sure that there's order log n scheduling. So this is not 01, but it's still very fast, and it doesn't have these complicated heuristics. And so, for instance, if the targeted latency is 20 milliseconds, which is everybody runs after 20 milliseconds, 2 CPU-bound tasks with the same priority, basically each get 10 milliseconds. You can use nice values. So 2 CPU-bound tasks separated by a nice value of 5. The low one gets 5 milliseconds. The other one gets 15. Together, those work out. 40 tasks each get 1 millisecond. That's no longer fair, etc. So CFS has this property that it's much less dependent on complicated heuristics. And it gives you fair fractions of the CPU. Now, I haven't told you a lot about this because we don't have a lot of time. You can make your judgment as to whether you think this is easier to think about than a bunch of arbitrary heuristics. I think it is. All right? It's sort of all about giving each task its own virtual CPU that runs at a certain speed and then just doing that, okay? And it's all about adjusting the speed. And, of course, now we're back to a little bit of heuristics. But this is likely what you're running in your Linux kernel if you run in Linux, okay, is CFS. All right, so the last topic about scheduling I really want to talk about is real-time scheduling. And so in real-time scheduling, our goals are completely different. So remember our goals at the beginning of this lecture. I either want to do I want to optimize for responsiveness, or I want higher throughput, or I want to get fairness maybe. But this idea of responsiveness or throughput is all about run it as fast as you can to make people happy. Okay, different goals, but all about making things fast. Real-time scheduling is not about fast, it's about predictable. When I slam on my brakes in my car, I want it to predictably stop the car in a certain amount of time, okay? I want the brakes to be applied in 100 milliseconds, regardless of what else is running. If suddenly my car's brake system is running and computing the 5,000th digit of pi and I slam on the brakes, I still want 100 milliseconds, okay? So it's about predictability, not about performance. And that changes the equation, okay? And there's a couple of things here to keep in mind. So hard real-time says I have a set of deadlines for my tasks, and for each task, it always completes in a well-defined deadline. And if I fail in any deadline, that's considered a major failure. Okay, so hard real-time schedulers are in things like cars or heart monitors at a hospital. Things where failure to meet a deadline could result in, death, for instance, right? So hard real-time can be very important. There are many schedulers. I'll mention EDF for earliest deadline first in a moment. But many have been looked at. Soft real-time is like hard real-time, but softer. That's good that people are listening. Okay. So, what does soft real-time mean? Soft real-time means that I mostly make all my deadlines. If I miss one or two, a little bit, nobody's going to die. I might get a little glitch in my Game of Thrones video I'm watching or whatever it happens to be. I don't know, the latest Billie Eilish video, whatever is going on here. Something like this, right? So, I think the idea here is if you're watching videos or other things where there's not life and limb involved, it's about trying to do your best to mostly meet the deadlines. And if you mostly meet the deadlines and you only occasionally miss a video frame or only occasionally miss an audio frame, humans are not going to notice. It's going to be okay. They call it soft real-time. So what's interesting these days is combining hard and soft real-time in the same system, because basically what happens is you get a single system that can both make sure your brakes always go off properly, but maybe the video in your car or the audio in your car doesn't miss any deadlines, okay? And so that's a type of real-time scheduling of interest. And so here's an example of how we think about real-time scheduling. And again, we don't have a lot of time on this, but tasks are basically preemptible in the real-time world, independent with arbitrary arrival times. They have deadlines and computation times. So here's an example where we have task 1, 2, 3, 4. Task 1, notice, arrives here. It has a certain amount of computation and then a deadline there. So I have failed in my scheduling if my computation goes past the deadline. That's called a failure, okay? And I just put these different tasks 1, 2, 3, 4 in this picture to show that they all have different arrival times. Time goes like this, by the way. And they all have different deadlines. And you might say, how do I schedule this? And you could say, well, let's try round robin. Okay? And if you try round robin, what you find out is, not surprisingly, it doesn't keep the deadlines, because round robin has nothing to do with deadlines, right? I mean, it's alternating. Okay? What's better is what's called earliest deadline first, which is preemptive priority-based dynamic scheduling. And the idea here is very simple. Here we have tasks where they take period 4 with 1 computation. This has period 5 with 2 computation. This has period 7 with 2. And if I go ahead and say this guy arrives and runs for 1, this guy arrives and runs for 2, and notice the deadline here is 4 away. Okay, and so notice this guy met its deadlines, this guy met its deadlines, this guy met its deadlines. And then if I keep running this out, but I always run the task whose deadline is closest to expiring, that's what it means, earliest deadline first, then it turns out I will actually meet the deadlines, as long as I'm not, the blue, if you sum it up, isn't more than 100% of the CPU. So EDF is actually a very nice scheduler. If you want to talk more about this, come by office hours sometime, we'll chat. But this is one that's kind of the baseline scheduler that everybody talks about. All right. So I think we're about done for now. Let's say in conclusion, we talked about scheduling a lot. So we talked about round-robin scheduling, where you give each thread a small amount of the CPU time when it executes and cycle between all the ready threads. It's good for short jobs, much better than FIFO. We talked about the shortest job first, or shortest remaining time first, which is run whatever job has the smallest burst time. Of course, that means you're predicting the future. Maybe you use a Kalman filter. Maybe you use some other schedule or some other technique for predicting it. It's optimal, but of course, it's hard to predict the future. It's unfair. We talked about multi-level feedback scheduling, which was definitely one of the types of heuristics used in a lot of early operating systems. Many queues with heuristics for going between the queues, high priority at the top, lower at the bottom. Think of this, and I leave this with you to think about it again, as an approximation to SRTF, because I'm kind of predicting the future. I'm putting the short jobs up and the long jobs down, and it gives me kind of an approximation, right? We talked about lottery scheduling, where it's a type of fair queuing almost, where we're giving lottery tickets to each task. We talked about the CFS scheduler, which is active use with all you right now, which is a form of fair queuing. And we started talking about real-time schedulers such as EDF, guaranteeing behavior by meeting deadlines. Real-time tasks are actually defined by repeated tuples in typical case. And we'll talk maybe more about schedulability tests after the exam. But I'm going to say good luck, everybody. Thursday, unfortunately, we're spread across 5 rooms, so there'll be a lot of you I don't see on Thursday. But I wish you the best of luck, and looking forward to seeing you in a week on Tuesday and getting back to work. Plan, if you can bear it, to stick around, because there's going to be some really good information given at the review session. So, ciao. Say it again.
Why do you need things other than earliest deadline?
Well, because earliest deadline first is really optimizing for deadlines, but a lot of jobs you're not really optimizing for deadlines. You want to get responsiveness or something. So it doesn't quite give you what you need. What's up?
Hey, do the processes themselves determine the deadline, or is the schedule determine what's a deadline?
So what I've shown you so far is that the processes have to know their deadline. And so what often happens is there's some thanks for mentioning that. I forgot to say that. I will next time. There is a whole very complicated analysis that people do in the compiler to try to compute the actual amount of compute time. And then the deadline